Hello guys, in this video we will see a simple neural network model. This project will help us strengthen our NN skills and will complement our learning of neural networks. So let's get started. Project Credit Default Prediction using a simple neural network. Goal. The goal of this project is to build a simple neural network, NN, model to predict whether a client will default on their credit card payment in the next month. We'll go step by step through data preprocessing, preparing and cleaning the dataset, model building, defining a basic feed-forward neural network, training and evaluation, checking how well the model predicts credit default. Project structure. This project is divided into two main files for clarity and reusability. Data preparation to handles data loading, cleaning, normalization, and splitting into training test sets. Credit default NN to builds, trains, and evaluates the neural network using the processed data. Dataset used. Source default of credit card client's dataset, UCI. Contains information about 30,000 clients from a Taiwanese bank. Features include demographic info, age, gender, education, etc. Credit card data, limit balance, bill amounts, payment history, etc. Target variable, default payment next month. 1 equals defaulted, equals not defaulted. Neural network overview. We'll use a simple feed-forward neural network that learns to detect patterns between clients, characteristics, and their probability of defaulting. In summary, the process will be load and pre-process the dataset, split it into training and testing sets, train the NN model, evaluate performance and accuracy, data preparation. This notebook demonstrates the complete data preparation workflow for the Credit Default Prediction Neural Network project. Overview. Download UCI credit card default dataset. Exploratory data analysis. Data cleaning and pre-processing. Feature engineering. Train test split and scaling. But first of all, let's better understand the data. This is a crucial step that a lot of data analysts and scientists may ignore, which is a big mistake. You're not just crunching some numbers that your boss gave you, you are trying to make sense of them. So you need to start by understanding them. Let's head to the dataset description. I will not read what's on the screen here, but I encourage you to pause the dataset information and variable descriptions and get back to the video. Now let us start by getting the data from the UCI ML repository using the code provided by them. Let's look at the dataset shape. We can see that we have 30,000 samples with 23 features. Remember to go and read them if you haven't yet, and the Y variable, which is our target one. Now that we have the data, let's perform some exploratory data analysis to see what we have and decide if we need to perform some preprocessing. By the way, 99.99% of the time, we do need to perform some form of data preprocessing, aka the data is always messy or at least needs some adjustments to be correctly implemented into our model. We can see that all our data is of 64-bit integer type. Now I want to see the distribution of our target variable. Oops, we can see that there is class imbalance, 77.9% to 22.1%, or for every row with default in Y, we have 3.52 samples with no default. Let's keep exploring, but we need to get back to this note. Now looking at the distribution of the different X variables, we can see that there is no real issue and everything looks logical. Here's a task for you. Do a correlation analysis by performing a correlation matrix. Now back to our independent variables, let's check for outliers. We can see that there are many variables that we need to decide what to do with so they don't mess with our model's predictive ability. Again, another note that we have to come back to later. We know that we have no null values, but I checked anyway. It's good practice. Summary of our EDA. Exploratory Data Analysis Summary. Dataset shape, 30,024. Total features, 23. Target variable, y. Default rate, 0.221. Class imbalance ratio, 352:1. Key insights. Dataset has 30,000 samples with 23 features. Target variable shows class imbalance, ~361 ratio. Features include demographic, payment history, bill amounts, and payment amounts. Payment history features pay 0 to pay 6, show payment delays. Bill amounts and payment amounts have wide ranges with potential outliers. Some features may be highly correlated, e.g., consecutive bill amounts. Next, SDPS. Handle outliers in bill and payment amounts. Consider feature engineering for payment patterns. Scale features for neural network training. Split data into trained test sets. Data preprocessing and feature engineering. The three key preprocessing steps identified in our EDA start with outlier handling for bill and payment amounts. Strategy. Bill amounts use winsorization at the 99th percentile plus log transformation. Payment amounts cap at the 95th percentile while preserving zero payments. Winsorization at the 99th percentile means values lower than the first percentile are replaced by the first percentile value, and those above the 99th are replaced by the 99th percentile value. Same logic applies to the 95th. We also scaled our data using standard scaler to ensure that no single feature dominates the distance calculations in an algorithm, which can help improve model performance. This is the output, as we can see, for both bill and payment amounts. Now for the target variable, we will use the SMOTE method, which addresses imbalanced datasets by creating new synthetic data points for the minority class. In this example, the default class. We can see that we added 13,382 synthetic data points, and the balance ratio became 1. Finally, we export this data so we can import it in our NN training file. This is a good practice. It avoids performing these steps each time, especially with large datasets that take time to process. NN training step. Now, in the NN training step, let's look at the model architecture. Input 23 features scaled. Hidden layers 64 to 32 neurons with dropout. A neural network regularization technique that prevents overfitting by randomly deactivating or dropping neurons during training. Output 1 neuron sigmoid for binary classification. Loss binary cross entropy. Optimizer Adam with learning rate scheduling. So load the artifacts we just created, define the model, train, and test it. Beat my accuracy, I got 80%, tweak, test, and learn. So that's it. You may ask, where the model training I clicked on the video for? That's not what's actually important here, it's all standard. What's more important is data preprocessing, depending on the context we are in. So please try and do it yourself, and don't forget to like and subscribe.